hard to see.
Yes, thank you. Thank you.
Okay, so welcome back to the afternoon session.
Okay, so let me remind you, in the morning we consider this semilinear elliptic equation with a power of u here, and then if f is sufficiently small, then this is the Dirichlet problem is well posed. You consider that there is a nonlinearity m bigger or equal than 2, and in that case, the partial data problem, meaning that you have two, the Dirichlet map is the same for functions supported in an open set, and this is measured in the open set. In that open set gamma here, then you can recover the potential. As I mentioned before, this is not known for the linear problem. So you have m equal to 1. This is not known. And if you linearize, therefore, linearizing doesn't help because it's the same equation. So in the case m equal to 2, we did a second order linearization, and this is exercise. You get this identity, which is in the same spirit as the previous identities used for the Calderon problem. But the difference is that these are three functions. Well, we only need two, in fact, but you get three, and all of these are harmonics with the support contained on the boundary, and the support at the boundary containing gamma. So that's the main difference. The support here is in this open set that can be very small. Right. And then using this theorem that I mentioned before, is you have in general H U V equal to 0, U and V are harmonics. This is the partial data analog of the Calderon linearization, but support of U and V at the boundary is contained in gamma. Then this implies H equal to 0. So that's the main result that one uses to prove this, and then you get that this is time B3 is equal to 0. Somebody asked me about this last step. I didn't really. You can take any harmonic function which is non-zero. There are many such. The thing is that the set where the harmonic function is 0 is a set of measures 0. This is a theorem for harmonic functions. So you get Q1 equal to Q2, right? Since it's sufficiently regular outside the set of mature 0, therefore everywhere. So that's the idea of the proof. And for higher order linearization, you can do higher order linearization if you have a higher power instead of m equal to 2, 3, 4, whatever you want. Okay. Okay, so this was for the potential problem. For the Calderon problem itself, with partial data, so you have gamma equal to here. Suppose here there should be, this is, unfortunately, is the wrong picture. I don't know why, what the wrong, so you have the set gamma 1, and you have the set gamma 2. Can be arbitrary open sets, it can be disjoint, or can be the same. So it can be arbitrary open non-empty set. Forget about this picture. So you measure the normal derivative on gamma 2, on this one. In the current, you measure it here. And the voltage is supported here. So 0 is grounded on the rest support of the voltage. And if so this is the Calderon problem with partial data. I did not talk much about this when I was talking about the Calderon problem because I was planning to do it later, and this is the time. And this is the open problem. Can you recover gamma? And in the case gamma 1 equal to gamma 2 in 2 dimensions is solved, but otherwise it's not solved. I mentioned it before. But if they are disjoint, for instance, it's not solved. And in dimension bigger or equal than 3, it's not solved. I will mention this as a problem tomorrow. I will write it more explicitly. There are some partial results. So if gamma 1 is the whole boundary, and gamma 2 is essentially, this is the normal. This is the vector C, suppose starting on the south pole. From now on, you will write the south pole up, right? Everyone here? And so this means you're taking half of the, suppose this is a ball, this is half of the domain essentially. This restricts the set. This is epsilon is a positive number. This is a unit vector in the sphere. And so this is half of the sphere. And then, in that case, you can solve this problem with this data here. Again, this picture is the wrong picture. You have 2 sets, gamma 1 and gamma 2. And here also gamma 1 is missing. Oh, gamma 1 is just here, the complement of gamma 2. Yeah, right. So this is, again, this is a generalization of that result. You consider the point x0, which is outside this domain. Assume it's strictly convex for simplicity. So this is the illuminated set. So you shine light here. This is the illuminated set. This is the dark part, called the back face. This is called the front face. And if gamma 2 is the front face, where it's illuminated, and gamma 1 is a small neighborhood of the complement of gamma 2, so a little bit bigger than the complement of gamma 2. So you measure, there is some intersection here, then you can recover the conductivity in that case. So this is a partial result. It's not, in particularly here you're taking directly data on one part and Neumann data in the complement. So you have data everywhere. So suppose gamma 2 is smaller, in dimensions 3 or higher, we don't know. Right? So this is a very important problem and it's not solved. When omega, the nice thing about this result is that by taking the point x0 to be as close as you want to the domain, you can get this set as small as you like. So it can be arbitrarily small. Here, in the result with Buchheim, this is not arbitrary by any means. For instance, in the case of a ball is half of the domain. Okay. Now for semilinear conductivities, so the gamma depends on x and u. You have these conditions that this is analytic. By the way, this type of conductivities show up in applications that are called varistors, where the conductivity depends on the potential, changes with the potential. And I'm assuming that this conductivity has a power series expansion in U. So it has U squared, and so on. And it's sufficiently regular. And the first term is 1, so that's the Laplacian. That's very important because we're going to linearize and we're going to get the Laplacian. This problem, again, for small enough data is well posed. That's the problem usually with nonlinear equations, that you have to assume some smallness for some problems, not all problems, to guarantee uniqueness and existence of the solution. Otherwise, there are singularities development. Now this is the right picture. You take an arbitrary open subset of the boundary, and you take the Dirichlet-Neumann map associated to this. So here, the support and the measurements are going to be in the same set. And the result for the partial data problem is that if this is true, then the conductivities are the same. And no stability result has been shown for this, so that would be a nice problem to work on, what kind of stability you get from this uniqueness proof. But this is the first partial data result for nonlinear conductivities. But this is arbitrary. In dimensions 3 or higher, we don't know this result. In dimension 2, we know it for the linear problem. So again, this is has been the topic of, for the nonlinear case, the nonlinearity gives you more information. Usually, nonlinear equations are harder to solve, but for the inverse problem, they help you. So the idea of the proof is to, well, you write it in the power series expansion. It starts with 1, plus the convergent power series here. These are sufficiently regular. And then you want to prove that all of these terms are the same, right? Because it's analytic in this variable, in U, so it has a power series expansion in U. And then again, you take the mth linearization, can be 2, 3, etc. And f is an L infinity function. You get an identity. This is typical for these problems, but these are harmonic functions. Again, this is the same phenomenon that we had before. That's why I mentioned it before. This is, of course, more physical. And you have some identity involving harmonic functions, products or gradients of harmonic functions, and you sum over this. Of course, this can get messy as m gets larger, but the support of this is again the same that we had before. The support of these harmonic functions is contained in this fixed open set. Then, in order to prove that, you need to prove that f is equal to 0, and one uses similar method to the ones used for this result. So I will mention this. For instance, in the case m equal to 2, you get this identity, Q1 minus Q2, orthogonal to the products of the gradients. This is very similar to what we had with Calderon. Remember the Calderon linearization? I keep doing this. I had to change the. So I'll learn. Oh, sorry. Will that work?
Yep.
Okay, remember Calderon linearization? When you have the quadratic form, you send gamma to the Q gamma of f, which is integral of gamma gradient u squared, where u solves the equation. And use the boundary. So this is the power that you need to, and then to maintain the potential F on the boundary and the linearization. This was one of the exercises. Gave you that the integral in the direction h, gradient u, no gradient v equal to 0, where u and v are harmonics functions. And then you show that h equal to 0 by taking u equal to e to the x dot rho, and v equal to e to the minus x dot rho conjugate, where rho in Cn, rho dot rho is equal to 0, right? But here, these exponential solutions don't work because they are supported everywhere on the boundary. And you need that these harmonic functions be supported in the set gamma 1. They are 0 outside of the set gamma 1 when you're making the measurements. Where this is, so these are supported here. They are 0 in the complement of gamma 1. So it's the same thing. You take base 3 to be non-zero, and then you use the fact that this product of gradients is dense. This is what we show for harmonic functions with that vanish outside the open set. Okay, so it's the same, it's exactly the same situation that you get here, but of course, it's just more messy. Okay, and so when you have two conductivities, gamma 1 and gamma 2, sufficiently regular, you take the Dirichlet to Neumann map. This is lambda are constant, so you're linearizing around constants now. Is equal to this. Again, the support of F is contained in an open subset of the boundary. And lambda can be arbitrary. It's just because this is a solution of the equation, divergence, which is not true for the potential case. So U constant, which is called lambda there, is a solution, right? Because we're just taking the gradient of U. Okay. So we have the same result. That from the partial data, you can show that gamma 1 is equal to gamma 2. Okay. Yes.
Gamma depends on gradient U.
Yeah. Ruirui will talk exactly about the quasi-linear case. It's coming up immediately. So I'm lazy and I ask Ruirui to finish my lecture today. So this is the main result that I just mentioned, that if you have the products of gradients of solution of harmonic functions, this is exactly the analog of Calderon. You see, Calderon was, I know what the problem is. I'm doing this. I think I know how to do it. Why is it so big? So how do I move it down? Slowly, okay. This is Calderon, sorry. Oh. So this is the same thing, but again, the difference is that the support is contained in gamma. Okay, so now we will start with quasi-linear. This is the question you were asking when gamma depends on x, u, and the gradient of u. So this is quasi-linear because the nonlinearity is in the highest order terms. Okay. Oh, right.
So do you know which one is displayed for? Both? That's the
Okay. Why is this? Is that okay? The volume? Okay. So thank you very much for organizing this conference. It is really helpful. And thank you for the opportunity that I can try doing a presentation. So today I'm going to talk about the Calderon problem with quasi-linear and isotropic connectivity. So first, let's review a little bit Calderon inverse problem. We denote the potential by U and the conductivity by gamma. And we consider this boundary value problem, which is given by the divergence equation and the boundary condition of the voltage potential. We perform the measurements on the boundary where we can find the voltage on the boundary as well as the current on the boundary. And then we can define this so-called Dirac to Neumann map. We have seen it a lot. So F is the potential on the boundary, and the result of this mapping, it becomes the current on the boundary. And the Calderon inverse problem asks, does this lambda gamma, the DM map, determine the connectivity uniquely? And we shall also review some technical detail about the CGO solutions. So we construct these very strong solutions. I should, yeah. Does this work? Okay.
The screen is too bright, so nobody. So
I see.
you use
Okay. Yeah. Okay. Is this okay? So this wave-like solution, we have an amplitude A and a remainder R. The amplitude A satisfies this transport equation, and this remainder R satisfies this estimate. So we see if we let k equal to 0, we actually get the H0 norm, which is L2 norm of R, can be bounded by 1 over c norm times this thing. So we have a 1 over c norm estimate, which is really helpful. And now let's look at the Caldron problem with cosilinear connectivity. For the cosilinear connectivity, the connectivity does not only depend on the space variable x, but also on the potential u and possibly gradient u, as we'll talk later. And for the connectivity depending on the space variable x and potential u, we have the result given by Sun in 1996, where we assume this Holder regularity on connectivity, and we show that the DMAP uniquely determines this cosilinear connectivity. And the proof is basically based on this first order linearization. If we denote gamma xt with a fixed t by gamma tx, then we can turn to consider for the linear problem by this linearization formula. So what our assumption now is that the DMAP agrees for the cosilinear connectivity, which is this DMAP. And by this formula, we see that for each fixed t, the DMAP agrees for cosilinear connectivity gives us the DMAP agrees for the linear connectivity. So we are able to utilize the uniqueness result for the linear connectivity. And next, we may also look at some results in cosilinear connectivity that also depends on the gradient of the potential. And this theorem is proved by Kastia, Faiz Mohammadi, Kian, Krupchik, and Uhlmann. It says that for dimension n larger or equal to 3, we may assume the connectivities are smooth in the space variable and real analytic in other variables. So this assumption is for doing the Taylor expansion in the proof. And then the result is that we have the uniqueness determination given the DMAP. And I'll talk about the sketch of the proof since the proof of our result is utilizing the similar idea. So this one is the Taylor expansion for the connectivity. And use this expansion, we can linearize the problem and obtain such a long integral identity. So this actually contains all the higher order linearizations, because given different m, the integral identity comes from different order of linearization. And in this identity, we denote this difference between the derivatives of the connectivity by t. And this gamma 0 is defined to be the value of gamma 1 x0, which shall be equal to gamma 2 x0 just by performing the first order linearization. And these solutions u are just solutions to the divergence equation here. And as an example, we briefly look at what happens when m equal to 1 and m equal to 2. For m equal to 1, the long integral identity becomes this identity. And we are basically using the fact that the product of the gradient of the CGO solutions are dense in L2, so that we can prove all the T0 up to Tn are equal to 0. For m equal to 2, this is the integral identity we have. And now we are construct CGO solutions more carefully, but the idea is very similar as in the linear problem. So we first set the amplitudes A to be supported near a ray. And this is for later we are doing the inverse Fourier transform near this ray, on this ray. And also our solutions just have this CGO, traditional CGO form. And we are choosing those phase C and amplitude A wisely so that they are indeed solutions and we can use the estimates for the remainder. And I'll briefly mention here that this method does not work for n equal to 2 for the same reason as in a linear problem. Because when we are choosing those C and A, there is no enough freedom in n equal to 2. Yeah. Sorry, which one do you mention? Oh, sorry. This is the permutation. Yeah, thank you. Okay. And now let's head into the anisotropic problem. So I think Gunther mentioned it on the first day. Let's do a brief review. There exists a natural obstruction in the uniqueness determination in an anisotropic problem. That is, if there is a diffeomorphism, which is an identity map on the boundary, and we define the push forward of the connectivity A by this diffeomorphism, by this formula, then the new connectivity, the push forward connectivity, will have the same DN map as the original connectivity. So it means that we can only determine the connectivity up to this diffeomorphism. And in dimension 2, we have isothermal coordinates, which can reduce the anisotropic case to the isotropic case. So I'll briefly state the isothermal coordinates result. So this is in complex analysis. If sigma is such a 2x2 matrix, bounded and positive definite, then there exists a diffeomorphism F, which has this asymptotic behavior as z goes to infinity, such that the push forward by F of the original connectivity sigma will be a multiple of identity matrix. So that can be viewed as isotropic connectivity. So this is basically a change of variable formula. Okay, so let's also look at some anisotropic cosilinear results. The first one is given by Sun and Uhlmann in dimension 2. So we consider cosilinear matrices, cosilinear connectivities, that is anisotropic, which is a matrix, and they depend on space variable x and potential u. So in this case, if we assume some Holder regularity, then the DN map determines the connectivity up to a diffeomorphism. And this second result is for dimension n larger or equal to 3. In this case, we need to assume in addition that the connectivities are real analytic. And in this case, there exists a real analytic diffeomorphism such that the connectivities are determined up to this diffeomorphism. And I mentioned here that these results depend on linearization, so the regularity may depend on the regularity result in linear case. And by that time, the linear case haven't been improved to the best. So actually now we have also better result for those anisotropic cosilinear case because we have better regularity for the linear case. Yeah. Where is the H? Oh, the diffeomorphism, like push forward relationship. Yeah, thank you. Okay, so I'll also briefly mention the schedule proof for those anisotropic cosilinear problems. So as same as before, we denote this ATX to be the AXT. So this is a linear connectivity from determined by this cosilinear connectivity. And as similar as before, we use this first linearization. And by the result for the linear and isotropic case, where we consider the DNN map for a linear connectivity, but is anisotropic. For each fixed t, there will exist a diffeomorphism phi t, such that the one connectivity is the push forward of the other by this phi t. But note that this result holds for each t. So now, currently, we don't have any guarantee that this phi t will be the same for each fixed t. So what we want to prove now is that phi t is independent on t. So this can be reduced to show the time derivative or the second variable, like derivative of each connectivity will agree when t equals to 0. And this reduction is by differentiating the original equation with respect to t. And to prove this, we will need the second order linearization. So this formula is what we get after performing second order linearization. And we see that the right-hand side of two connectivity will agree because our assumption is that the DN map for two connectivities agree. So by assumption, we know this identity holds, where this capital BX is the difference between two connectivities, the difference between the time derivative of two connectivities, evaluating at t equals 0. So now our goal becomes, given this identity, can we prove capital B is equal to 0? The solutions to the original equation at linear case. Okay. Then the method of proving that is some density. To prove some density result as following, I will just mention the statement of those results. Yeah, the first one is the density of the gradient of product of two solutions. And the second result is the density of the product of the solutions themselves. Okay, so now we'll head to the main result we'll focus on today is cosilinear and isotropic problem in dimension 2. So I think we have seen that we can prove for cosilinear connectivity in dimension n larger or equal to 3. And we also see the result for cosilinear and isotropic connectivity in dimension 2. So our result focus on what is not proven. It's just that the cosilinear and isotropic connectivity, but in dimension 2. So it's just under the similar regularity, we can determine the connectivity up to a diffeomorphism given the same DN map. And the main idea of the proof consists of the following steps. First, we will reduce to isotropic case using isothermal coordinates. And second, we also do the higher order linearizations, and we actually arrive at the same integral identity we have seen before. And next, we will do a boundary determination using singular solutions. This is a preparation for the next step. We can use Buchheim's sigil solutions as well as limiting Karaman weights to apply the method of stationary phase. So for time reason, I may quickly skip the boundary determination step. It's just using those singular solutions and plug them into the identities to get that the T element in the integral identity here will vanish on the boundary up to infinite order. for all such elements. And then we will utilize these Buchheim-Sigel solutions, which is the very strong tool in dimension 2 Calderon problem. So Buchheim constructed Sigel solutions to the Schrödinger equation in dimension 2 by considering this system D plus Q U equals to 0, where D and Q are matrices and U is a vector. So we choose a holomorphic function psi, and D bar is, so if we're using complex analysis notation, D bar might be equivalent to say that F is holomorphic and partial F is anti-holomorphic. If we relates to the 2D dimension, then D bar should be some multiple of partial 1 plus or minus part. Sorry. Okay, thank you. And partial is okay. Yes. So we choose a holomorphic function and let this matrix phi be defined by this holomorphic function. And also we'll encounter this imaginary part of psi in the later construction. We call this function phi. And we'll seek solutions of this form, which is very similar as the Sigel solutions we have seen before. And before I present the exact form, I'd like to introduce the Cauchy operator, which is defined by this integral. And it satisfies D bar composed with D bar inverse composed with D bar is the identity. And similarly, we will see bar inverse, and this satisfies bar inverse composed with bar is identity. Partial. Okay. And for convenience, we will denote the composition of these two operators by bar partial phi inverse. And the Buchheim solutions have the form, so now we are returning from the vector to the scalar functions. This U is also having this form. However, this psi is a holomorphic function, and this V satisfies, I think in this case, partial V, actually D bar V is equal to 0, which is V is holomorphic. And the remainder has this explicit form, which can be written as an infinite series of operator S applied to the amplitude V. And this S is defined by two compositions of the operators we define here. So in the definition of R, we will encounter the composition of this operator and this operator. And we'll see later that this ensures that we have good estimates on the remainder term. And that is based on the estimates on these two operators, which is related to the estimates on the Cauchy operators. And this is just symmetrically, we have another set of solution of Buchheim, where we have anti-holomorphic amplitude, which just satisfies partial V equals to 0. And also this new remainder defined by ST. And Buchheim showed in his paper that for any U in L2 space, we have this L2 estimate for SU. So at least we know that the remainder R, the L2 norm of the remainder R can be controlled by H to the 1/3 power of itself. And later, Guillermo and Zhou showed that for any U in W1P space, there is some epsilon larger than 0 such that this operator satisfies these estimates. So remember that S is a composition of 2 of such operators. So if we get some estimates on this operator, we would be able to get some estimate on the remainder R. And for later use, I think I may record this estimate here. Okay. And then, we'll briefly mention how Buchheim used these solutions to prove the linear problem. So this is the theorem in Buchheim's paper, where it states that if the potential Q is bounded, then the Cauchy data set agrees, means that the potential also agrees. So the Cauchy data set is basically the version for Schrödinger equation of the DM map. Okay, so CQ is equal to the boundary value of U and the normal derivative of U on the boundary. And the data we know is, because this CQ is related to Q, is U is the solution to this Schrödinger equation. And the proof just used this key lemma, the density result, that shows the products of these Buchheim solutions are dense in L2. To prove this, we can just choose 2 specific Buchheim solutions. So we let the holomorphic function phi becomes z squared, and the other anti-holomorphic phase being minus z bar squared. And so that for any f in L2, this left-hand side will be equal to the right-hand side here, just calculate everything. And then if this is assumed to be 0, we want to show that f will be 0. And this can be done by stationary phase method, which I'll go through in the next slides. So the stationary phase method is a really strong method in microlocal analysis, which we just consider the oscillatory integral. And the interesting case is when we have a phase function with critical point. Because if the phase function has no critical points inside the support of the amplitude A, then by repeatedly integrating by parts, we have this oscillatory integral can be arbitrary small order, because this h is like going to 0, and if this holds, then this oscillatory integral gives very small quantity. So what happens when this phase has critical point at inside the support of A? So the classical result is given here, the stationary phase. And we need to define the signature of a Hessian matrix as this. So this D square denotes the Hessian matrix for the function phi. If it has k positive eigenvalues and n minus k negative eigenvalues, we define the signature to be k minus n minus k. And this theorem states that for any phi, the phase phi, smooth have only one non-degenerate critical point. Non-degenerate means the Hessian is invertible at that critical point. So we assume this phase function only has one critical point at x0. Then there are differential operators of order like this. So this is just representing a differential operator, and 2 nu is the order that is maximum, such that for every compact k inside the domain, this is U, and every natural number n, there exists a constant depending on this compact set and n, such that for every U in this space, we have the oscillatory integral can be controlled by an expansion, and actually this can go to infinity, but we just write the rest of the expansion by this estimate. It might look a little complicated, but I guess the most important is we know that this is an expansion in H. So, for example, if nu, we start with 0, if nu is equal to 0, and our dimension n is equal to 2, then the first term in this expansion is H times this exponential times U evaluating at x0. Because when nu equals to 0, this differential operator has order 0, so we are just looking at the original function u itself. And also, because in our case, our phase function is z squared, where when you have the critical point, it's just z equals to 0, and your phase is also equal to 0, z squared is equal to 0. So phi 0 is equal to 0 here. So this term just gives us 1. So we only have a h times u x0 for the first term in the expansion. And for the time reason, I may not be able to go through like every key element of the proof. So basically, we are just using this Morse lemma to reduce to a specific case of stationary phase, which is called quadratic stationary phase. And this is the specific version for the quadratic stationary phase. And basically, we are using Fourier transform as well as the Taylor expansion for the exponential function to prove this case. And then the general case can be proven from this. So let's look at an example using stationary phase, which is just the identity in Buchheim's paper, and he used this for proving linear problem. So we have seen this some minutes ago. By stationary phase, we see that this term inside the integral will be of h times f0 times some constant c and plus some lower order terms. And now we can control the remainder terms by the remainder estimate. So we actually have a Cauchy inequality here implicitly. Remember what we have for R is that we have this estimate. So this, if we apply this on R immediately, it might seem not sufficient because this is only 1/2 plus an epsilon. But what we want is 1 plus epsilon, because our main term starts with order h, and we want that to be higher order of h, because h is going to 0. But if we can move one partial phi inverse to the other part, like, let me... Because we remember that RH is defined by an operator S, which is a composition of 2 such partial phi inverse. So we may move one partial phi inverse. It takes a little effort to check this is can be done by regular integration part. So I think that gives us to some like z square minus z bar square over h f. So we just move that partial inverse inside partial phi inverse to the other part by integration by parts. And what's left is an exponential term, might not be exact, but something like this. And the remaining thing in R, we just call it SH. So there should be another partial phi inverse. SH should be another partial phi inverse something. So the L2 estimate for SH can also be given by this estimate. So by Cauchy inequality, this first term gives us L2 estimate of h 1/2 plus epsilon, and this SH L2 can also give us another 1/2 plus epsilon. So by this detailed analysis, we see that all the integral from here involving the remainder term can be given these estimates. So we indeed have this principal term is of the highest, largest size. So we can show that f0 is equal to 0. And similarly, we can show that f vanishes at all the other points. Say we take z minus x0 square instead of z square in the solution, then it is possible to be done. Okay. And then we'll discuss how that helps us solve our problem, which is the difference is we have a different integral identity because the conductivity is cosilinear. So first, it would be very natural to try just the same solutions as we have seen before. But unfortunately, it turns out that the remainder estimates are not good enough because we are taking the derivatives. As an example, we look at the m equal to 2 case, and we have, this is not the one in m equal to 2. So this is the identity we finally get for m equal to 2. So we mentioned briefly here, by choosing those solutions equal to 1 and also u1 equal to 1, we would get integral identity that already appears in the previous case. So if we assume the previous case has already been solved, then we can just let those, we have those are 0, and this is what we obtain afterwards. So we just, originally this is jk equal to 0 to 2. Now it's jk from 1 to 2. And now we let those solutions to be the ones we have seen before, and we focus on the term in the expansion of this whole thing where the derivatives all hit the faces. So the solutions have an exponential and the exponential has a face. So by some detailed computation, we actually have a feeling that those derivatives hit the faces will give the largest size terms. And by stationary phase, on this identity, on this quantity, we actually have a capital C over H. So this 1 over H force comes from differentiating the phases. Because once you differentiate a phase, you will get a 1 over H. And if all the derivatives hits the face of those 4 solutions, then you would get a 1 over H force. And this z square, z bar square also comes from differentiating the phase. And how come this is C over H? That is because in the stationary phase theorem, we see that when we are evaluating that function, z square, z bar square at 0, many terms will disappear because you are evaluating at 0. For example, the first term is itself, so z square, z bar square is equal to 0. And the second term is given by applying this second-order differential operator on z square, z bar square, and something we want to recover. So we are actually is just applying this operator to z square, z bar square, and something we want to recover, and evaluating at z equals to 0. If we just apply this differential operator for one time, we will still get something vanishes at 0. And it turns out we must at least apply this differential operator for 2 times, which means inside the identity here, this nu shall at least be 3 when we get something that is non-zero in the expansion. So, actually, for this case, 2 is enough. So nu equals to 2, and n is equal to 2. So we get a h cube here. And h cube divided by h fourths give us c over h. However, if the derivative hits the 1 over this term, instead of the face, for one of the solution, we will get some quantity like this. And inside this quantity, we look at the term involving the remainder, RH. And similarly as before, this 1 over h cube comes from differentiating 3 faces, and this z bar square comes from that 2. And we now look at the best estimate we have for RH. This is actually h1 plus epsilon, as we have seen before, by integration by parts. Then this term has order h minus 2 plus epsilon, where for the previous one we have 1 over h, which is h minus 1. So we cannot guarantee minus 2 plus epsilon is larger than minus 1. So we cannot utilize those solutions directly. And the solution is we choose phase function with no critical point. And this solution has very similar form as the ones we have seen before, except that we choose z plus 1 over 2z squared over h. And we implicitly assume that this function has no critical point inside the domain. That depends on your domain. So actually, we can always find some capital constant c plus c z squared, such that this function has no critical point. That depends on the size of your domain. So without loss of generality, we assume this has no critical points in the domain. And what's good about this is that by integration by parts, we have this formula. And we see that this holds for any f in compact supported, and for any phi that has no critical point inside the domain, we can use Calderon-Zygmunt estimate to find this LP estimate. So the Calderon-Zygmunt is for this second term. The first term is obviously is of order OH. So up to here, we see that the RH and SH, where we mentioned briefly in the previous step, so for the new solutions we see here, RH L2 might be OH as well as SH, which is something inside RH. And we'll see how that helps us solve this problematic case. And I just mentioned here, this idea of choosing phase without critical point has already appeared in limiting Karaman weights. What's special in our case is that in dimension 2, we have this explicit form for the remainder, so that we can write out everything explicitly to make the largest power of these solutions. So we come back to the same integral identity, and now we choose the new solutions in this way. So we observe that the new solutions, when we multiply them together, adding the faces together, we still get the same z squared minus z bar squared. So that we can do the stereo phase as before. However, this time when we are taking derivatives for the faces, we get something 1 plus z minus 1 plus z instead of z bar like that. So we can always extract a principal term just by extracting 1 minus 1, 1 minus 1, 1, 1, 1, 1. So that gives us the principal term. And this time we have a 1 over h cube order because the solution phase, it doesn't vanish in the first term. So h over h fourth, we have a 1 over h cube. So it's very promising that we can control the remainder terms. And it's not difficult to check that the integral involving the remainder term are capital O 1 over h squared. We can see that briefly here that in this case, our new integral term involving the remainder, as before, we do one time of integration by parts and write it as then this is still capital O h 1/2 over epsilon is autonom. Well, this SH has better estimate. It is capital OH. So they add up to have a power order larger than h 1 plus epsilon. So again, this is h1 plus epsilon divided by h fourth, where we have a higher order of h, so that they are indeed of smaller size, the remainder terms. That's how we can extract information about the principal term, which is very clean. We just have a T11 plus T22. And similarly, we can choose other sets of solutions properly and get a system of linear equations. For example, for m equal to 2, this is what we extract when we choose 3 sets of solutions. And the proof for other m is also similar. So that's how we solve this baby problem. And thank you very much for listening.
And so, anyway, this yeah. So because you use expansion, you need Taylor series should be valid at the beginning. Right?
Yes.
So if the nonlinearity gamma with respect to this gradient u
It's not.
small, then it's completely different story.
Yes.
I was thinking the gradient, the MREI gradient u has value for nonlinearity compared to small completely different.
Thank you.
Several typos.
Oh, really?
You write the equation the wrong way, isotropic the wrong way, anisotropic the wrong way.
It's so difficult for me to notice typos. Maybe I'm just
See?
too careless.
This one is correct. Those are isotropic and a different solution to solve. There were several cases. Let's check after topic solution. It seems like that. Maybe they will ask you to post this.
Yeah, I think you want me to
So-
send it to the organizer.
Yeah, but check the spelling first.
Okay. Thank you.
Yeah, thank you.
Good job.
Thank you for doing it.
Thank you very much.
Oh, that's impressive. Clearly, clearly some command.
And doing it in our fourth year.